In this video, we look at how we can use integration to find centres of mass. And this video has been prepared to support the work in Unit 6 of the WJC for the mathematics specification. The specification says that we need to be able to find the centre of mass of uniform rigid bodies and composite bodies, including the use of integration. So, for a rigid body which is a lamina, we can find the centre of mass of a uniform lamina using integration, and the results given here should be known. For a solid body, which is a body of revolution, if we have a solid which is obtained by rotating the curve y equals f of x between x equals a and x equals b fully around the x-axis, then we need to be able to find the x-coordinate of the centre of mass. And we can do that by evaluating the integral between of a and b of x times y squared, integrated with respect to x, and then divide it by the integral between a and b of y squared, integrated with respect to x. The y-coordinate and the z-coordinate of the centre of mass will each be 0 by symmetry. And there is a similar result for the volume of for a uniform solid which is obtained by rotating a curve around the y-axis. You should certainly know how to use these results to find the centre of mass of a solid cone or a solid hemisphere. So for our first example, we've got to prove by integration that the centre of mass of a uniform lamina, which is 1/4 of a circular disc with centre O and radius r, is distance 4√2 over 3 pi times by r from O. So, what we'll do is we'll start off by considering part of the circle x squared plus y squared equals r squared, which lies in the first quadrant. So if we take the area enclosed by that quadrant of the circle, together with the x-axis and the y-axis, we have got 1/4 of a circular disc. The integral between 0 and r of y with respect to x is simply the area underneath the curve. Well, we know that the area of a circle is pi r squared, so the area of a quarter circle is going to be 1/4 pi r squared. The integral between 0 and r of x times y integrated with respect to x is going to be the integral between 0 and r of x times by the root of r squared minus x squared. And in order to work this integral out, we need to make use of a substitution. So if we make the substitution u equals r squared minus x squared, then that gives me du by dx is minus 2x. So we can say that x dx is going to be the same thing as minus 1/2 du. When x is 0, we've got u equals r squared, and when x is r, we've got u equals 0. So when we make the substitution, we obtain the integral from r squared up to 0 of the root of u, that's the root of r squared minus x squared, has just become the root of u, and the x dx has become minus 1/2 du. Root u is the same thing as u to the half, so I've got to integrate minus a half u to the half. When I integrate that, I end up with minus a third u to the 3 upon 2, with an upper limit of 0 and a lower limit of r squared. So put the limits in, we've got 0 minus a third r cubed, so we've got 1/3 r cubed. So we've obtained the two integrals that we need in order to work out the x-coordinate of the centre of mass. So the x-coordinate of the centre of mass is the integral of xy with respect to x divided by the integral of y with respect to x, which gives us 1/3 r cubed divided by 1/4 pi r squared, which simplifies to 4r over 3 pi. So we've got the x-coordinate of the centre of mass is 4r over 3 pi. Now the shape that we have got has the line y equals x as a line of symmetry, which means that the centre of mass must lie on the line y equals x. So that means that we know that the centre of mass must be the point 4r over 3 pi, 4r over 3 pi. And the distance of the centre of mass from the centre of the circle, which is the origin, is d, where d is the square root of 4r over 3 pi squared plus 4r over 3 pi squared. So that gives me the square root of 32r squared divided by 9 pi squared, which simplifies down to 4r over 3 pi times root 2, which is what we had to prove. Now in part B of the question, we have a uniform lamina ABCD, which has been formed by cutting an isosceles triangle OAD from 1/4 of a circular disc with centre O and radius 4 meters, as shown in the diagram. First thing we have to do is we have to find the distance of the centre of mass of the lamina from the line AD. We're dealing with a lamina. It's useful to set up a variable which gives us the surface density of the lamina. So we'll suppose that the surface density of the lamina is sigma kilograms per metre squared. If we look at the triangle OAD and introduce M as the midpoint of AD, we know that the triangle OMA is right-angled and that it has a hypotenuse of 2, and that each of the smaller angles in the triangle are 45 degrees. So we've got an isosceles right-angled triangle OMA. So we know that OM is equal to OA. We also know that OM squared plus MA squared must equal 4. So put that together, we've got 2 lots of OM squared must equal 4. So OM squared must equal 2. So OM must equal root 2. If we let G1 be the centre of mass of the triangle OAD, then we know that G1 is 2/3 of the way along the median from any corner of the triangle to the point which is the midpoint of the opposite side. So O to G1 is 2/3 of the way from O to M, so OG1 is 2/3 of root 2. And if we let G2 be the centre of mass of the quadrant of the circle, so that's the whole shape going O to A to B to C to D back to O, then from the first part of the question we know that OG2 is 4 root 2 over 3 pi times by 4, which is the radius, so that is 16 root 2 over 3 pi. And from those two results we can set up now a process to find the centre of mass of the blue lamina. So we'll set up the x-axis to be the line joining O, G1, M and G2, in other words the axis of symmetry of our shape. So for the first part, the quarter disc we know has got an area of a quarter times pi times 4 squared. So that's 4 pi, so its mass is going to be 4 pi sigma. Now, the centre of mass for the whole quadrant is the point G2, and we know the distance OG2, in other words the x-coordinate of that centre of mass, is 16 root 2 over 3 pi. So the sum of the mx's for the components is simply going to be 4 pi sigma times 16 root 2 over 3 pi, which gives me 64 root 2 divided by 3 times by sigma. Now for the triangle that we're cutting off, this is the triangle OAD that we're cutting off, the area of that triangle is simply going to be a half times 2 times 2. So that is an area of 2 meters squared. So the mass is going to be 2 times sigma. We have already determined that the centre of mass of the triangle ABC is the point G1, where OG1 is 2/3 of root 2. So the x-coordinate of the centre of mass of OAD is 2/3 root 2. So the sum of the mx's for the triangle OAD is going to be 2 sigma times by 2/3 root 2, which gives me 4/3 root 2 times by sigma. Now the lamina that we've got is the quarter disc minus the triangle OAD. So the mass of the lamina is going to be 4 pi sigma, take away 2 sigma, in other words 4 pi minus 2 lots of sigma. And the sum of the mx's for the lamina is going to be 64 root 2 over 3 times by sigma, take away 4 over 3 root 2 times by sigma, which ends up giving me 20 root 2 times by sigma. The centre of mass for the lamina, therefore, is the sum of the mx's for the lamina divided by the mass of the lamina, so that's 20 root 2 sigma divided by 4 pi minus 2 lots of sigma. The sigmas cancel, so we've got 20 root 2 divided by 4 pi minus 2, which gives us the centre of mass, the x-coordinate of the centre of mass there is 2.6768. So the distance of the centre of mass from AD is the distance of G2 from M, and that is going to be 2.6768, take away root 2, which gives me 1.2626 meters. Now, when the lamina is freely suspended from the point A, the line joining A to the centre of mass will be vertical. We know that the centre of mass is on the line of symmetry and it is 1.2626 meters below from the line AD. So we've got, for the triangle consisting of A, M and the centre of mass, we know that A to M is root 2 and we know that M to the centre of mass is 1.2626. So the angle theta on the diagram is given by tan theta equals 1.2626 divided by root 2. In other words, theta is 41.7 degrees. We know that angle OAD is 45 degrees. So the angle, the acute angle between OA and the vertical is 45 plus theta. So that is 87 degrees to the nearest degree, which means that the obtuse angle between AB and the vertical is 93 degrees. Now move on to our second example. We have the finite region bounded by the x-axis, the curve with equation y equals 2e to the minus x, the y-axis and the line x equals 1 is rotated through one complete revolution about the x-axis to form a uniform solid. We have to prove that the volume of the solid is 2 pi times 1 minus e to the minus 2 and find in terms of e the x-coordinate of the centre of mass of the solid. We know that the volume of revolution for a curve that is rotated about the x-axis is given by the integral. Is given by pi times the integral of y squared integrated with respect to x. So in this case we have got pi times by the integral between 0 and 1 of 2e to the minus x all squared, which is pi times the integral between 0 and 1 of 4e to the minus 2x. 4e to the minus 2x integrates to give me minus 2e to the minus 2x. And if we substitute in the upper limit and then the lower limit, we've got pi times by minus 2e to the minus 2, take away minus 2. In other words, we have 2 pi times by 1 minus e to the minus 2, which is what we were asked to prove in part A. For part B, we've got to find the centre of mass, or the x-coordinate of the centre of mass of the solid. So we need to recall the result that says for a uniform solid obtained by rotating the curve y equals f of x between x equals a and x equals b, fully around the x-axis, then the centre of mass is given by x bar as the integral of between a and b of xy squared divided by the integral between a and b of y squared. Now in part A we found out that the volume of the solid of revolution was 2 pi times 1 minus e to the minus 2, and the volume of a solid of revolution is simply pi times the integral of y squared dx. So, in other words, from part A we know that the integral of y squared dx is 2 lots of 1 minus e to the minus 2. So we don't need to do any more integration at all for the denominator of a fraction. For the numerator, we need to work out the integral between 0 and 1 of x y squared. So that is the integral between 0 and 1 of x times by 4e to the minus 2x. And to integrate this, we're going to need to use integration by parts. So starting off, we'll leave the x alone and we'll integrate the 4e to the minus 2x. So we've got x times minus 2e to the minus 2x. Then we need to take away the integral of the derivative of the x, which is 1, times by the integral of the 4e to the minus 2x, which is minus 2e to the minus 2x dx. So that's a standard integration by parts. When we substitute in the limits for the first part, we first of all get minus 2 times e to the minus 2, take away 0. And then we have got still to add on the value of the integral between 0 and 1 of 2e to the minus 2x. So that's going to give me minus 2e to the minus 2 plus 2e, the integral of 2e to the minus 2x is minus e to the minus 2x. And I want the value of that when x equals 1, take away the value of that when x equals 0. So that's minus 2e to the minus 2 plus minus e to the minus 2 minus minus 1. In other words, 1 minus 3 lots of e to the minus 2. So we can now say that the x-coordinate of the centre of mass is going to be 1 minus 3e to the minus 2 divided by 2 lots of 1 minus e to the minus 2. As far as the question is concerned, that will be more than satisfactory as an answer. We've answered the question. We've given the x-coordinate of the centre of mass in terms of e. For the first part of our final example, we have to prove that the centre of mass of a right circular cone of base radius r and height h is distance h over 4 from the centre of mass, from the centre of the plane face of the cone. If we start off with the line y equals r over h times x, then we have a straight line through the origin, which when x equals h, we've got y equals r. And if we rotate that around the x-axis, then we're going to end up with a cone whose base has radius r and whose height is h. Now again, we have the result that for the centre of mass of a solid obtained by rotating the curve y equals f of x completely around the x-axis is given by the integral of xy squared divided by the integral of y squared. So we've got two integrations that we need to do. So the integral of y squared between 0 and h is going to be the integral of r squared over h squared x squared between 0 and h, which gives me r squared over h squared times x cubed over 3. When we put the upper limit in, we get r squared h cubed over h squared times 3. In other words, we get 1/3 r squared h. And when we put r x equals 0 in, we get simply 0. So the value of the integral of y squared is 1/3 r squared h. We also have to work out the integral of xy squared. So that's the integral of x times by r squared h squared over x squared, because we know that y is r over h times x. So we've got to integrate r squared over h squared times by x cubed, which gives me r squared over h squared times by a quarter x to the 4, with limits of upper limit of h and lower limit of 0. Put the upper limit in, we get r squared over h squared times h to the 4 over 4, which simplifies to a quarter r squared h squared. Put the lower limit in, x equals 0, simply gives me 0. So we've got the integral of xy squared is 1/4 r squared h squared. So we've got the x coordinate at the centre of mass is 1/4 r squared h squared divided by 1/3 r squared h, which gives me 3/4 h. So the distance of the centre of mass from the origin is 3/4 h, which means that the distance of the centre of mass from the centre of the circular plane face of the cone is going to be 1/4 h. We then have a uniform solid S consists of 2 right circular cones of base radius r. The smaller cone has height 4h, and the centre of the plane face of this cone is O. The large cone has a height of kh, where k is bigger than 4. The 2 cones are joined so that their plane faces coincide. The point A is a point on the circumference of the common base of the 2 cones. And the first thing we have to do is show that the distance of the centre of mass of S from O is h over 4 times by k minus 4. So let's define our x-axis as being the obvious direction, our line of symmetry for the shape solid S. We'll suppose that the solid has got a density of rho kilograms per metre cubed. And we can now set up our little table to try and work out the centre of mass for the combined solid S from our knowledge of the centre of mass of the first cone and the second cone. The first cone has radius r and height 4h, so its volume is 1/3 times pi r squared times 4h, so that's 4/3 pi r squared h, so its mass is its volume times by the density, so that's going to be 4/3 pi r squared h times rho. The centre of mass for the first cone is going to be 1/4 of the height of the cone away from O, so the centre of mass is going to be 1/4 of 4h away from O in the positive direction. In other words, it's going to be h. So the sum of the mx's for that first cone is going to be 4/3 pi r squared h times rho times by h, which is going to give me 4/3 pi r squared h squared rho. For the second cone, which has a radius of r and a height of k times h, the volume is going to be 1/3 times pi r squared times kh, so the mass is going to be 1/3 pi r squared kh rho. The centre of mass for cone 2 will be 1/4 of kh away from O, but it's in the negative x direction. So the centre of mass for cone 2 is has an x coordinate of -1/4 kh, which means that the sum of the mx's for cone 2 is going to be -1/12 of pi r squared, k squared, h squared times rho. Moving to the combined solid, by adding the results of the mass and the sum of the mx's for cone 1 and cone 2, the total mass of the solid S is 4/3 pi r squared h rho plus 1/3 pi r squared k h rho, which simplifies down to 1/3 pi r squared h times 4 plus k times rho. Moving on to the sum of the mx's for the solid S, we have 4/3 pi r squared h squared rho minus 1/12 of pi r squared k squared h squared rho. So if we take a factor of 1/12 pi r squared h squared rho out, we end up with 1/12 pi r squared h squared times 16 minus k squared times by rho. So for the solid S, the centre of mass is going to satisfy x bar as the sum of the mx's divided by the total mass. So that's the 1/12 pi r squared h squared 16 minus k squared times rho divided by 1/3 pi r squared h times 4 plus k rho. The 1/12 and the 1/3 will cancel out to leave us with 1/4 on the top. Pi r squared h squared will cancel the pi r squared h to leave me just with h on the top. And the rho's will cancel as well. So we're ending up there with 1/4 h times by, well, the factorisation of 16 minus k squared is 4 plus k, 4 minus k, divided by 4 plus k. So we're ending up with x bar is h over 4 times by 4 minus k. Or in other words, minus h over 4 times by k minus 4. Because we know that k is bigger than 4. That means that x bar is negative because we know that both h is positive and we also know that k minus 4 is positive. So we've got a negative value of x bar. So the distance of the centre of mass for the solid S away from O is simply h over 4 times k minus 4. And the final part of the question says that when the solid is suspended by a string attached to A and hangs freely in equilibrium, the angle between AO and the vertical is 30 degrees. We're told that R is 2 times H. We have to find the value of K. Well, there's our x-axis again. We know that the centre of mass of S is on the negative side, with the distance of G from O being h over 4 times k minus 4. If the solid's hanging in equilibrium from A, then the line A to G must be our vertical line. And we are told that the angle that AO makes with the vertical is 30 degrees. So in the diagram that we've got there, we've got theta is 30 degrees. So we've got tan 30 must equal GO divided by AO. So we've got tan 30 is 1 over root 3 equals a quarter h times k minus 4 divided by r. But we've been told that r is 2h. So we've got 1 over root 3 equals a quarter h times k minus 4 divided by 2h, which rearranges to give me k equals 4 plus 8 over root 3, which finishes the question off.